Hello friends, welcome to this YouTube channel. Today we are going to solve a numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip when values of parameters of its exact equivalent circuit are given. A 440 volt, 50 Hz, 6-pole 3-phase star-connected induction motor has following per-phase parameters referred to stator side. R1 equals to 0, X1 equals to 0.7 ohm, R2 dash equals to 0.3 ohm, X2 S dash equals to 0.7 ohm and Xm equals to 35 ohm. The rotational losses amount to 750 watts. Using exact equivalent circuit, we have to calculate stator current, stator power factor, power input, air gap power, mechanical power developed and power output. We also have to compute developed torque, shaft torque and overall efficiency when the motor runs at speed of 950 revolutions per minute. Let us first write down the given data. Number of poles of the machine P equals to 6 and supply frequency F equals to 50 Hz. Let us now determine synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 6, that gives us 1000 revolutions per minute. Given motor speed Nr equals to 950 revolutions per minute. Expression for slip S equals to Ns minus Nr divided by Ns. Using values we get 1000 minus 950 divided by 1000, that gives us 0.05 per unit. For stator winding, given resistance per phase R1 equals to 0 and leakage reactance per phase X1 equals to 0.7 ohm. Stator impedance per phase Z1 equals to R1 plus JX1 equals to 0 plus J times 0.7 ohm. For rotor winding, given resistance per phase referred to the stator R2 dash equals to 0.3 ohm and standstill leakage reactance per phase X2S dash equals to 0.7 ohm. For any value of slip S, expression for rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. We have determined slip S equals to 0.05 per unit. Therefore, Z2 dash equals to 0.3 by 0.05 plus J times 0.7 ohm, that is equal to 6 plus J times 0.7 ohm. This may be written in polar form as 6.0407 ohm at an angle 6.6544 degree. For shunt branch, given magnetizing reactance per phase Xm equals to 35 ohm. Let us now calculate Jxm plus Z2 dash. Using values we get 6 plus J times 35.7 ohm. This may be written in polar form as 36.2 ohm at an angle 80.4596 degree. Now we shall compute equivalent impedance per phase. ZDQ equals to Jxm parallel with Z2 dash, that is equal to JXM into Z2 dash divided by JXM plus Z2 dash. Using values we get 35 at an angle 90 degree into 6.0407 at an angle 6.6544 degree divided by 36.2 at an angle 80.4596 degree, that gives us 5.84 ohm at an angle 16.1948 degree. This may be written in Cartesian form as 5.6083 plus J times 1.6288 ohm. Let us now determine total input impedance per phase. Zin equals to Z1 plus Zdq. We have obtained stator impedance per phase Z1 equals to 0 plus J times 0.7 ohm. Using values we get Zin equals to 5.6083 plus J times 2.3288 ohm. This may be written in polar form as 6.0726 ohm at an angle 22.55 degree. Given line-to-line terminal voltage VL equals to 440 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254 volts. We have computed total input impedance per phase Zin equals to 6.0726 ohm at an angle 22.55 degree. Now we shall calculate stator current per phase. I1 equals to ET divided by Zin. Taking terminal voltage per phase ET as reference, we get I1 equals to 254 at an angle 0 degree divided by 6.0726 at an angle 22.55 degree. That gives us 41.827 ampere at an angle minus 22.55 degree. Let us now calculate rotor current per phase referred to stator side. I2 dash equals to JXM divided by JXM plus Z2 dash into I1. Given magnetizing reactance per phase XM equals to 35 ohm. We have computed JXM plus Z2 dash equals to 36.2 ohm at an angle 80.4596 degree. Using values we get 35 at an angle 90 degree divided by 36.2 at an angle 80.4596 degree into 41.827 at an angle minus 22.55 degree. That gives us 40.44 ampere at an angle minus 13 degree. Expression for air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.3 ohm, and we have computed slip S equals to 0.05 per unit. Therefore, Pg equals to 3 into 40.44 square into 0.3 by 0.05, which is approximately equal to 29,437 watts. Let us now determine mechanical power developed. Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.05 into 29,437, which is approximately equal to 27,965 watts. In polar form, stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 41.827 ampere at an angle minus 22.55 degree. For star connected induction motor, stator current per phase equals to stator line current. Now we shall calculate stator power factor. Cos phi 1 equals to cos of 22.55 degree, that gives us 0.9235 lagging. For three-phase induction motor, total input power Pin equals to root 3 times VL into I1 cos phi 1. Using values we get root 3 into 440 into 41.827 into 0.9235, which is approximately equal to 29,438 watts. We have determined mechanical power developed PM equals to 27,965 watts. Now we shall compute total output power PO equals to PM minus PR. Given rotational losses, PR equals to 750 watts. Therefore, PO equals to 27,965 minus 750, that is equal to 27,215 watts. Expression for overall efficiency of this motor, eta equals to PO divided by Pin. Using values we get 27,215 divided by 29,438, that is equal to 0.9245 per unit or 92.45%. Expression for developed torque TD equals to PG divided by 2 pi into ns by 6t. We have computed air gap power PG equals to 29,437 watts. Therefore, TD equals to 29,437 divided by 2 pi into 1000 by 6t, which is approximately equal to 281 Newton meter. Expression for shaft torque TSH equals to PO divided by 2 pi into NR by 6t. We have obtained total shaft power output PO equals to 27,215 watts. Therefore, TSH equals to 27,215 divided by 2 pi into 950 by 6t, which is approximately equal to 273.56 Newton meter. Now we shall compute the equivalent rotor current I2 dash using Thevenin's theorem. For this purpose, we shall remove the load, that is the equivalent rotor impedance Z2 dash, from this circuit. Now, the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. We have obtained stator impedance per phase Z1 equals to 0 plus J times 0.7 ohm. This may be written in polar form as 0.7 ohm at an angle 90 degree. Rotor impedance per phase referred to the stator Z2 dash equals to 6 plus J times 0.7 ohm, that is equal to 6.0407 ohm at an angle 6.6544 degree, and shunt impedance per phase Z0 equals to JXM equals to J times 35 ohm. This may be written in polar form as 35 ohm at an angle 90 degree. Let us now calculate Z0 plus Z1. Using values we get 0 plus J times 35.7 ohm. This may be written in polar form as 35.7 ohm at an angle 90 degree. Now we shall determine Thevenin's voltage. VThevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get 35 at an angle 90 degree into 254 at an angle 0 degree divided by 35.7 at an angle 90 degree. That gives us 249 volts at an angle 0 degree. To determine Thevenin's impedance, let us short circuit the voltage source. Now, the impedance as seen from terminals A and B is our Thevenin's impedance. Z-Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 35 at an angle 90 degree into 0.7 at an angle 90 degree divided by 35.7 at an angle 90 degree. That gives us 0.68627 ohm at an angle 90 degree. This may be written in Cartesian form as 0 plus J times 0.68627 ohm. Let us now calculate Z-Thevenin plus Z2 dash. Using values we get 6 plus J times 1.38627 ohm. This may be written in polar form as 6.158 ohm at an angle 13 degree. We have obtained Thevenin's voltage. VThevenin equals to 249 volts at an angle 0 degree, and Thevenin's impedance Z-Thevenin equals to 0.68627 ohm at an angle 90 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2 dash, back to this circuit. Now we shall determine the load current or the rotor current per phase referred to stator side. I2 dash equals to IL equals to VThevenin divided by Z-Thevenin plus ZL, or VThevenin divided by Z-Thevenin plus Z2 dash. We have computed Z-Thevenin plus Z2 dash equals to 6.158 ohm at an angle 13 degree. Therefore, I2 dash equals to 249 at an angle 0 degree divided by 6.158 at an angle 13 degree. That gives us 40.4352 ampere at an angle minus 13 degree. Let us now calculate induced EMF per phase. E1 equals to Z2 dash into I2 dash. We have obtained rotor impedance per phase referred to stator side Z2 dash equals to 6.0407 ohm at an angle 6.6544 degree. Therefore, E1 equals to 6.0407 at an angle 6.6544 degree into 40.4352 at an angle minus 13 degree. That gives us 244.257 volt at an angle minus 6.3456 degree. We have determined induced EMF per phase E1 equals to 244.257 volt at an angle minus 6.3456 degree. This may be written in Cartesian form as 242.76 minus J times 27 volt. Now we shall calculate stator current per phase. I1 equals to Et minus E1 divided by Z1. We have obtained stator impedance per phase. Z1 equals to 0.7 ohm at an angle 90 degree. Using values we get I1 equals to 254 minus of 242.76 minus J times 27 divided by 0.7 at an angle 90 degree, that is equal to 29.246 at an angle 67.4 degree divided by 0.7 at an angle 90 degree. That gives us 41.78 ampere at an angle minus 22.6 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor at a particular slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.